So we were doing random variables, and the reason we started random variables is the following: that that previously we were doing many distributions, many different distributions, and they were all developed out of Bernoulli trials, right? Out of Bernoulli trials. That's one thing. Then the key thing was, the key difficulty was, we kept on creating new sample spaces. We kept on creating new sample spaces, new sample spaces for each new distribution, for each of them, each distribution. And once we did that, what happened was that we were answering same questions on different frameworks. So that was the process we were doing. Then we said, no, we don't want to do this. We want to work on one sample space. So then we want to work on one sample space. We want to work on one sample space, and then define functions on them. And then using these functions, answer all the questions. Using these functions, answer all the questions. All the relevant questions. That's where we were. That's how we motivated the concept of need for random variables. That's how we started random variables. I had various examples last time. So the way we defined random variable was, we said a random variable is a function x from. So our first thing was, random variable a function x from a sample space S to the real line. We will call any such function a random variable. It's a temporary definition. So any such function is a random variable. That's what we called it as. Then we showed another interesting fact, that is, if S is a sample space, P is a probability on it, and X is a random variable from S to the real line. We showed the following fact. You look at Q of an event B on the real line as the inverse image of the events given by X, then Q defines a probability on R, right? Q defines a probability on the range of X. And that's one thing we discussed last time. Then we came to the idea of what a discrete random variable was. So we said a discrete random variable X is from S to T, where S is a countable space, countable or finite, equipped with probability. Equipped probability T, right? And so is T. T is also countable, of course. If X is countable, S is countable, T is countable. Countable subset of R of the real line. Then we called X as a X is called a discrete random variable. The assumption that S is countable can be relaxed, but T has to be countable for sure. Then an important concept we discussed was this probability mass function of X. So we look at this function fx of t as the chance that X is equal to T. And this is called the probability mass function of X. So that's where we were at in some sense. And then one advantage was that this implies that if you want to understand the chance that X is an event A, you just have to do the summation over T in A, F sub X. So any event concerning X can be gotten from F. So this is where we were at last time. So let me just so the idea was random variables were required so that we could work on one sample space. We need not work on many sample spaces. And a discrete random variable is one where the range is discrete, that is, the range is countable, subset of real line. And it has an important parameter, that's probability mass function of X. But fx of t was probability X equal to T. And chance that X takes any event A is just the sum of this. And then we also said that if you have two random variables X and Y, so X is from S to T, Y is from S to T, and these are two discrete random variables. Then we said that X and Y have equal distribution. Equal is defined this way. Equal distribution if the chance of X equal to T is the same as chance of Y equal to T for all T. This is something that one has to learn. That's how you identify two random variables as being the same in some sense. The distribution of them are the same. So the word distribution is signifies that they have the same probability mass function. So that means they have the same probability mass function. They both have the same probability mass function. Okay, very good. So that's where we were at last time, and I had just begun independence. So let me just understand, go back again. Okay. So now in today's class, we'll try and understand independent variables. So independent random variables. So independence is a key concept in probability, right? So it's one of the key defining features of probability. Right? So before we recall from before that we discussed the following idea. We said that two events A and B are independent if the probability of A and B split up into probability of A times probability of B. And this is the definition of independence. And this is kind of a crucial idea in probability, right? Because this gave you the following idea that this was kind of equivalent. So is kind of equivalent, this had actually 2 to the 2 equations that is hidden inside it. And it gave, the observation we gave last time was this because this actually was equivalent to the fact that the chance of A given B was the same as chance of A, chance of A given B complement. It gave you 2 equations on either side, and also gave you the chance that B given A is same as probability of B is same as probability of B given A complement. So it's kind of a key idea in problem that this equation that we have here at the start told you that one event doesn't affect the outcome, probability of outcome of another event. And to generalize this, we also said that for any A1, A2, AN, n bigger than or equal to 2 are independent. It's not enough to just look at just A1 and A2 and AN was the product of I equal to 1 to n P of AI. This is not the only equation to look at. You have to do a little bit more tricky. So you would do put, I put an epsilon I at the top, epsilon 1, epsilon 2, epsilon n, and I put an epsilon I, where A super epsilon I was equal to, so epsilon I was, let's say, equal to 0 or 1, and A super epsilon I was either equal to A if epsilon I is equal to 0 or equal to 1, let's say, and A complement if epsilon I was equal to 0. So you have to take all these combinations to show these are the 2 to the n equations here for independence of n events. This is what we discussed a long time. So now you have 2 random variables. So you can understand they are functions of 2 random variables. They talk to sample spaces, sorry. And you know that they are the same law if the probability of x equal to t is same as probability of y equal to t. Now, you can also try and understand when are 2 random variables independent or dependent. So does x affect the outcome of y or y affects the outcome of x? So this can be generalized that the above notion can also be considered for random variables. Right? So, so you may have several different random variables. So this is key to understanding relationship between random variables. So you understand a relationship between random variables. So here's the definition. So the first definition that I will write down is the following. So its definition are 3.2.1. Right. So here this is called independence of random variables. Let me write that in maybe in green. So independence of 2 random variables. Okay. So here we say 2 random variables x and y. X and y are independent if x in A and y in B are these 2 events. So you take these 2 events, if the events x in A and y in B are independent for every event A in the range of x and every event b in the range of y. That's the definition of independence. So you have to check if every take any event a in the range of x, take any event a in the range of y, and then you have to check whether these two events are independent. That is, x in a and x in b are independent. So that equivalently, you can write it down in the following way: that is equivalently. So that is, so you check probability of x in a and y in b. That should split up as probability of x in a, probability of y in b for all a events a in the range of x and events b in the range of y. That's the idea. Very nice. So this one problem I'll give you in a homework problem. Or you can think of an exercise. Is the idea that independence is equal to the following idea. So if x and y are discrete random variables, sorry for that. So x and y are discrete random variables. Then x and y are independent if and only if. So you don't have to check for everybody, all events. It's enough to check for the following. You have to check probability x is equal to t and y equal to s is the same as probability x equal to t times probability y equal to s for all t in the range of x and s in the range of y. That's enough to check. This is some exercise that you can, I'll try and outline in one of the homework assignments, but this you can check. It's not that hard to check. You don't have to check for all events A and B. You can just check it for just these particular events, x equal to t and y equal to s, where t and s range over the range of x and range of y respectively. And then similarly, once you define this, let me just write down one more thing. You can define mutual independence of many random variables. So the same way we define for events. You can write the same way. So you can say this definition 3.2.3. You think of it as mutually independent random variables, mutual independence of random variables. You can think of it the following way. You say a finite collection of random variables x1, x2, xn are mutually independent if the sets xj, sets or events xj and xj are, so maybe sets I always define by bracket. Maybe this bracket is are mutually independent for all AJ, all events AJ, let's say, all events AJ, all events A sub j in the ranges of the corresponding X sub j. And similarly, like in the random variable case, J, you can say, as the events case, you can write again an arbitrary collection of random variables. XT, where T is in some index set I, for some index set I, uh, is mutually independent if every finite subcollection is mutually independent. That's one thing. So these are ideas that go into random variables quite easily, and then so let's do a couple of examples, and then idea will be more clear. So before we had this idea that we rolled a die twice, and we had this 36 outcomes, right? So then we worked with it properly and said that to identify events of the random variable and so on. So let's do examples. Example, let's call it 3.2.2. That's in the book. So the idea is that you roll a die twice. So you roll a die. So the idea was to roll a die 2 times, and that was the experiment. And then what we did was we viewed it as 36 outcomes, right? And then they were all equally likely. And so my handwriting is quite bad. Let's change it properly. So you roll a dice twice. And then the way we set it up was there were 36 outcomes. And we designated all of them as equally likely. Outcomes. And then we try to understand various events. But then now we come about the following way. Each roll's outcome. So now we can view each roll's outcome as a random variable. Each roll's outcome can be viewed as a random variable. And then you just think a little bit, then you think of it as, let's say, X is the outcome of the first roll. And Y is the outcome of the second roll. then from last class, you can easily check that X has the same distribution as uniform in the interval 1 up to, not interval, in the set 1, 2, 3, 4, 5, 6. And similarly, Y is also uniform 1, 2, 3, 4, 5, 6. This also you can see. And you also know the following, right? You also know the chance of X equal to X is equal to 1/6 for all X in the range of X, which is just 1, 2, 3, 4, 5, 6. Similarly, you know the chance that Y equal to Y is equal to 1/6 for all Y in the range of X, range of Y, sorry, 1 up to 6. And more crucially, we also know the following fact, right? We also know that they are both independent, because this calculation we have done before, that the chance of, let's say, X equal to X and Y equal to Y, that is the outcome in the first row was X and the outcome in the second row was Y, we already shown long time back that the same as probability X equal to X and Y equal to Y. This is true for all X in the range of X and all Y in the range of Y. So this is one simple example that we have seen of independent random variables. You just focus on the first role and the second role. They're both independent events, independent trials, and that forces X and Y to be independent. Very nice. So now this is sort of let's say we repeat an experiment many times. So suppose, so the above was only for two trials. So suppose we repeat an experiment. Let me write it down. Suppose we repeat an experiment n times for n bigger than or equal to 1, some n bigger than or equal to 1. And let's assume the trials are independent. Each trial of the experiment is independent. And then let xi denote the outcome of the outcome of the ith trial. Right? For I equal to 1 up to n. So from this, there's two immediate consequences. So one is, for any I in, let's say, 1 up to n, all xi have the same distribution that's one thing, and I not equal to j, xi and xj are independent. That's one immediate consequence, because each trial is independent. Moreover, this is just a immediate byproduct. You can also say that x1, x2, xn are mutually independent. That's the consequence of having n independent trials. So there's a notation for this. In such a case, one refers to these xi's. So in such cases, so let's call it, in such cases, one says x1, x2, xn are i.i.d. Okay, so the i.i.d. random variables. So here the first I is for identical, sorry, independent. First I is for independent, and this ID is for identical distributions. Distributed ID and identically distributed. So this is what i.i.d. Means, independent and identity distributed. That means the random variables are independent and they have the same distribution. So this is like has a very these are very interesting random variables that you repeated trials can be thought of as i.i.d. random variables. And this abstraction allows you to do many interesting calculations and understand. Let's do the following. Let's do a simple example. So let me do example 3.2.4. So here what I do is I say let x1, x2, xn be geometric p random variables, be i.i.d. random. Let's say, let me just say i.i.d. be a sequence of i.i.d. random variables. i.i.d. random variables such that each of, let's say, x1 has the same law as geometric p for some 0 less than p less than 1. So, but this means what? That means if they're i.i.d., that means everybody has the same law, right? So, that is, all random variables are geometric random variables with parameter p. So, suppose I want to understand what's the chance. Let's say ask you a question. That is, so what does this mean? I'm repeating n trials and I'm waiting for the time to get the first success. That's what geometric is, right? So let's just write this down. The background we have in our head, that is xi is the outcome of experiment I. Experiment I. And what is the experiment? The experiment is you repeat trials, or let's actually not use trials here because you find out, you observe the time taken for the first success. Right? And that's what this is doing. Let me write this in red. So I mean each xi is doing this following idea. So now what if I ask you the following question? So what is the chance? What's the probability? So let me write the question down properly. The question is, what is the probability that it took you at least j trials in each of the experiments? So what is the probability that all random variables are larger than j? J. For some, let's say j is some number, j is some number, j is some number bigger than equal to, let's say, one, some number. So what does it mean? What do you have to calculate? You have to calculate the following. That is, you want to find the chance that x1 is bigger than equal to j, x2 is bigger than equal to j, and so on and so forth, all the way to xn is bigger than equal to j. This is what you want. This is what you want. So how do you solve such a problem? So the first step one is you find the chance that one random variable. So first step one is you find the chance that x1 is bigger than equal to j. How do you do that for one random variable? How do you do that? So x1 is geometric p, right? Has the same law as geometric p, right? So I've been using tildes, or let me use the word tildes. So x1 has the same law as geometric p. Right? That means what? That means probability x1 equal to some letter k is the same as p times 1 minus p to the k minus 1 for k bigger than equal to 1. So the k minus 1 indicates there are k minus 1 failures and success at the kth trial. So the probability mass function is given by this for all k. So now, therefore, the chance that x1 is bigger than equal to j, that's going to be what now? Or let's say bigger than equal to j is going to be what is you look at the chance that x is equal to k, and you sum over all possibilities of k from j to infinity. That's what you're doing. But then you already know the chance of x equal to k is this expression. So you plug that in. So k equal to j to infinity p times 1 minus p to the k minus 1. And that's the same as p times the sum from k equal to j to infinity of 1 minus p to the k minus 1. This is a geometric series, and one can understand that those calculation as p times b by 1 minus r. B is 1 minus p to the so this k minus 1, 1 minus p to the j minus 1 divided by 1 minus 1 minus p. And that, if you do the calculation, you just get 1 minus p to the j minus 1. This is what you get. Of course, I've been a little bit loose in mathematical terms, so be a little careful. So when you do these computations, they're all limiting objects, so you should be a little careful. So they're all limiting objects, they're all series, and this computation can be made precise. Made precise. So if I've just manipulated series in an intuitive way, but you should be able to go back and right? They're all series. So you should think of them as limiting objects and do it for every partial sum and then finish the computation. Of course, I will not do this list. So now we know that everybody is of this form. But what did we want to calculate? We wanted to calculate the chance that x1 is bigger than equal to j, x2 is bigger than equal to j, and x1 is equal to j. So maybe I'll just rephrase the question a little bit. Instead of writing larger than j, to make it precise, I'll just write it as greater than or equal to j. This is what I'm doing here, this question. So now I have to compute this question. I know how x1 behaves there. So now step 2, you have to use independence. So use independence. Use independence. So what do you do here? You know that the chance that x1 is bigger than or equal to j up to xn is bigger than or equal to j. You observe what you observe. You observe that each of these events, x1 bigger than or equal to j, or let's say xi bigger than or equal to j, for all I equal to 1 to n, are events concerning xi. Right? So by independence, you know that this is the same as the product from I equal to 1 to n, the chance that xi is bigger than or equal to j. Right? And this we know. Now we use the fact that they are the same distribution. Right? We use the fact that they are identically distributed. And that gives you the product of I equal to 1 to n. They're all the same. They're all the same as start. So the 1 minus p to the j minus 1. That is, x1 has the same law as xi for any I. And now you have this doesn't depend on I. So it just comes out as 1 minus p to the j minus 1, the whole power n. So that's the chance of all of them being bigger. So this is one computation one. can do for independent variables. So chance that in n trials, if you look at the number of successes to be the first time to get the time taken to get the first success is at least j, then this is the computation.